function as in the previous equation, sum over all of the elements, and you have the LDIF. Okay, so what are the results and key takeaways of this approach? Well, first, there is just reconstruction fidelity when fitting a shape collection. So here we are auto-encoding the ShapeNet 13 test set, and we are sorting our results by our method's F-score, which is the curve in blue, and then we plot the SIF and OCNet reconstruction scores below. And you can see that across the board for easy shapes and hard shapes, the LDIF approach, because it's local, is able to improve in fidelity. Unseen classes are also a case where you see improvements for LDIF. So here we are auto-encoding several classes that have not been seen before during the training process, like pianos and printers. And the gap for LDIF compared to other approaches actually grows. And you can think of the reason for that as being because the approach is robust sort of at the part level, at a local level, rather than at the shape level. So since you have local independent encoding, you can do okay on parts you've seen before, even if they're part of a shape you haven't seen before, as long as your template is sort of reasonable. This can then be leveraged for slightly more practical applications like depth image completion, where LDIF is able to improve over other approaches on reconstruction quality. And there's also still this really nice property of structural consistency. So here we are independently passing the shapes through the LDIF architecture per frame, and you can see that even though there's no supervision on the fact that humans have arms and legs and those things are consistent, that the shape elements that come out of the training process based only on reconstruction are tracking the body parts in a very stable and consistent way. And so this sort of unsupervised learning of structural consistency is one of the big benefits of this approach. Efficient decoding is another benefit that in addition to improving reconstruction quality, the quality is improved with a decrease in the number of decoder parameters. And the decoder is the thing that has to get evaluated over and over. So because there's only 0.4% as many parameters, LDIF can be evaluated on a 128 cubed grid at 60 frames a second. And the reason that the network can be so much smaller is because it's describing only a local residual. So then the conclusions are that there are several specific advantages to adding structure to a deep implicit function. There's efficiency improvements from local encoding. There's generalizability improvements. In general, fidelity across the shape collection goes up. You get this nice property of learned correspondence, and then it's a human interpretable, sort of hybrid human interpretable representation. So thanks so much for listening, and enjoy the rest of your ICCV.
Thanks. Thanks for the nice presentation. We just have time for maybe one question. If anyone wants to ask, otherwise I have a question that might be interesting. So my question is, do you think this, since these ellipsoids are interpretable things, right? So you can directly edit the parameters if you want. Do you think these ellipsoids or this representation can be used for editing as well? So for example, what happens if you would move an ellipsoid to a different place, or would move them along a skeleton, for example, if you animate a person?
Yeah, that's a great question. I mean, we have experimented a little bit with that, not I think to this extent you're suggesting, but we did things like transfer the latent features from one shape to the ellipsoids from another shape. And it was a bit of a hit and miss kind of thing. You know, sometimes you actually could transfer the details reasonably, and other times the interactions between the neighboring ellipsoids, which are sort of nonlinear and not simple, would cause strange interactions. And so I think that if you did want to do that kind of, you know, interactive editing application, there's probably like a missing step that still needs to get added, which is to somehow have a better sort of more linear type of relationship between the things, or a simpler surface. You know, if you maybe were to use the ellipsoid weights to interpolate the latent shape rather than having them be a residual on top of this nonlinear function, I think you might be able to get nicer editing properties. But as it stands, I think that it's not like quite there. It's like interesting, but doesn't work.
Good. Yeah, thanks. Okay, I think we are short on time, so we have to move on to the next speaker. Songfang, if you want to take over.
Sure, thanks. You can share the screen while I introduce.
Yes, happy to.
Yeah, this one Pasadillo is a PhD student. Is a PhD student at the Max Planck ETH Center for Learning Systems, advised by Andreas Geiger and Luke Wankel. She has published well-received papers on interpretable shape representation, and we'll talk today about expressive 3D shape abstractions with invertible neural networks.
Okay, awesome. Can you hear me?
Yeah, I can hear you.
Fantastic. Okay, thank you very much for the kind introduction. And I would really like to congratulate the organizers of this workshop for the fantastic workshop that we had the opportunity to attend to. I think it's amazing. So far, I think it's one of my favorite workshops, across all the conferences that I have attended, virtual and non-virtual. So congrats, amazing work. Okay, so thanks a lot for having me today. Today I will talk to you about our recent CVPR 2020 paper, 2021, I'm sorry. And I would like to talk to you about how we can learn expressive 3D shape abstractions using invertible neural networks. Okay, so this is a joint work with Angelos Katharopoulos, Andreas Geiger, and Tania Fiedler. And as you can tell, the topic of my talk will be about primitive-based representation. So I don't think that I really have to convince you why we care about primitive-based representation, why are they useful. However, because I sometimes when I talk to people about primitives, the most the most question that I get, the most often question is why do we care? Why are they important? And with this slide, I will try to maybe explain a bit why I think primitive-based representations are important, and actually justify why I spend the majority of my PhD working exactly on this direction. Okay, so the first reason why I think primitive-based representations are important has to do with the fact that they are inherently parsimonious. This means that they are able to represent arbitrarily complex geometries using a small number of shape elements that typically have a semantic interpretation. This means that by simply looking at a part, you should be able to identify, figure out the functionality of the object part that this primitive represents. So what are the main challenges when it comes to primitive-based learning? So the first one has to do with the fact that we have a very few number of annotated data sets that contain primitive-based annotations. And this is one of the main reasons why there are so many works that try to tackle this problem in an unsupervised fashion. In addition to that, another challenge is related to the fact that ideally we would like to have a variable number of primitives where more complex parts are represented with more components, whereas simpler parts are represented with less primitives. And even though you might think that this actually is a trivial task, Based on my experience, I can tell you that this task is quite hard actually. And honestly, I don't have a good answer of how we could really learn the variable number of primitives correctly. So my intuition is that if we find the answer to this question, we will probably be then able to find an answer to this question, which for me is way more important, which is related to the it's a more of a philosophical question, and what I'm wondering is what really makes a part a semantic part. So all the work that we have done so far on with for primitive-based learning have mainly tried to generate, to recover more accurately, geometrically accurate primitives. However, we never explicitly enforce the semanticness on the final representation. Semanticness is just the emergent property. However, I have the feeling that this is very important, and we should probably think a bit about that for the next papers that we are going to work on. Okay, so one of my favorite papers about primitive-based representations is this very beautiful work from Pentland. He published this work back in 1986, and the idea here was that he used superquadratic surfaces to reconstruct this scene that you can see in this slide. And for this scene, he used 100 primitives, and the reconstruction required less than 1,000 bytes. So I think this is a very beautiful work, because up to this day, we don't have primitive-based representations that can efficiently reconstruct scenes. So I think I see this work as an inspiration of what we want to do next. So Subban Tulsiani was among the first that revisited the primitive-based paradigm in the context of deep learning, and he proposed to utilize cuboidal primitives, or more accurately, he proposed to learn cuboidal primitives using a neural network architecture directly from voxel-based representations of 3D shapes or images. And he trained this network without any supervision in terms of primitive annotations. As you can see here, while the abstractions are very cool, the actual parts and the reconstructions are not geometrically accurate due to the limited representation power of 3D cuboids. To address this, in 2019, we proposed to utilize superquadratic surfaces as geometric primitives. So the key idea behind this work, and this is why I think this is a nice step, was that instead of defining a priori the set of available shapes that someone could use, we proposed to learn a parametric family of shapes, and this allowed us to get more accurate reconstructions because the shape vocabulary was more diverse, while preserving the semanticness of the final representation. So as you can see from these results, the reconstructions are quite cute, but they are far away from the high fidelity reconstructions that we are used to seeing. And this has to do with the fact that in order to be able to get more accurate reconstruction with these kind of primitives, it is really important to increase the number of parts that are used. So recent works tried to address these limitations. So for example, Kyle before mentioned his work on SIF. Here I very briefly mention the CVXNet from the Young 10, where the focus was to utilize convex solids as geometric primitives, and they managed to get really high accurate reconstructions. However, in order to achieve that, they had to increase the number of primitives. Without a doubt, increasing the number of primitives comes at the cost of interpretability or semanticness of the final representation. So what we did in this project is that we identified that there exists a trade-off between the number of primitives and the reconstruction quality in primitive-based representations. So existing primitive-based representations that rely on simple shapes can get accurate reconstructions only if they increase a lot the number of parts as it is in the case of the CVXNet or SIP. However, this comes at the cost of semanticness or interpretability because, for example, if you see this visualization, this primitive-based reconstruction using convexes, if I show you this primitive, I think it's very difficult for someone to tell whether it belongs to a human part or a plane part. Therefore, to address this, we introduced neural parts, a primitive representation that is not limited to a specific family of shapes, and as a result, it can capture complex geometries using a small number of meaningful components. So existing primitive-based methods typically utilize a feature extractor architecture that directly predicts the primitive parameters. In this work, what we thought is that instead we defined each primitive as the deformation of a sphere that is conditioned on the input via this latent vector. And by having such formulation, we were able to have primitives that can when combined, can reconstruct arbitrarily complex genus zero shape. So the way that we defined the deformation is as a homeomorphic mapping implemented with an invertible neural network. Homeomorphic mappings have been implemented in the past using NLP. However, implementing the homeomorphism using an invertible neural network allows us to get the explicit mesh representation as well as the implicit occupancy representation for its primitive. So the input to our model is an image, and during training, our supervision comes from a watertight mesh of the target object that is parameterized as a set of surface samples and occupancy pairs. And we have a feature extractor that predicts a global feature representation for the input that is concatenated with a set of learnable per primitive embeddings. And we use a conditional invertible neural network conditioned on this per primitive embedding in order to learn a deformation from a sphere to M primitives and vice versa. So the coolest thing about using an INN is that we can easily compute the implicit and the explicit representation of its primitive. So for the implicit representation of the predicted shape, it is similar to previous work, the union of the per primitive implicit representation. So here you can see like the per primitive implicit representations. And in order to get, we can easily get the per primitive implicit representation using the inverse homeomorphic mapping and the implicit representation of a sphere, which is already known. For the case of the explicit representation, the way that we get the explicit representation is that we sample points on the surface of its primitive, and then using the implicit representation that we defined before, we discard the points that are inside one primitive. So during training, we seek to enforce that the surface of the target and the predicted shape will match, as well as that the orientation of the predicted and the target shape will match. Since we have access to the implicit representation of the predicted shape, we can also enforce that the volume of the target and the predicted shape can match. This is actually a very important loss. And moreover, we also add another loss term that prevents overlapping primitives. And finally, we have an auxiliary loss that prevents degenerate primitive arrangements. So let's have a look at how well does this whole method work. So I think that one of the main contributions that this work has is that it allows us to select the appropriate abstraction level based on our application without having to compromise abstraction to improve reconstruction. This is possible because neural parts decouple the reconstruction quality from the number of primitives, since regardless of the number of primitives, the reconstruction quality remains roughly the same. You can also see this here qualitatively, where we see that neural parts with 2 primitives get a relatively accurate reconstruction, whereas for the case, for example, of CVXNet, 2 primitives are not enough to capture fine details, and they are only able to focus on the object's structures. So we evaluate our model on the single view 3D reconstruction on dynamic Faust, and we see that the primitives are semantically meaningful and geometrically accurate, using an order of magnitude fewer parts than previous methods. So we use as simple as 5 parts, whereas this reconstruction will be 50 parts. This is another cool thing is that we preserve that neural parts preserve their semantic identity through a wide range of human motion. And since the same primitive is consistently used for representing the same object part. We also evaluate this work on organic shapes from Freihand hand. And what I really like about this result is that you can see that the network uses a single primitive for learning these prior and I'm sorry, for reconstructing this finger, whereas other models tend to have a hard time of capturing fine details. Of course, if we had increased the number of primitives for the case of CVXNet, the results would have been comparable to ours with 5 primitives. But what you lack is you lack the interpretability and the final representations are not meaningful. For the case of ShapeNet, we validate our model on various ShapeNet objects, and we see that with 5 primitives for the case, for example, of CVXNet, some parts cannot even be reconstructed, whereas with 25 parts, results are significantly better, I think these results are amazing. However, this comes at the cost of semanticness. So let me summarize what I presented here. So I talked about neural parts. Neural parts are a novel primitive representation that implements primitives as the homeomorphic mapping between a sphere and a target shape. And we implement this homeomorphism using an INN. And this allows us to easily define both the explicit and the implicit representation of a 3D, of the predicted shape. And since neural parts are defined through a homeomorphism, they do not impose any constraint on the predicted shape, and thus they can represent arbitrarily complex geometries. And this allows us to get accurate reconstructions while having a small number of primitives. So are we done? Can we go home? Is this finished? Definitely not. So one of the major limitations of our work has to do with the fact that the use of INN has a high computational cost. And as a result, if we would like to take this approach and use it for the case of scenes, which for me is the next thing to try, this method might be prohibitively expensive. However, I think still the idea and the concept is useful. And most importantly, I think that while we like to say that primitive-based representations are semantic, I think that they are actually spatial consistent. So for me, the next big thing in primitive-based representations would be an approach that would actually solve the problem of primitive-based representation, and the goal would not be necessarily to get geometrically accurate reconstructions, but semantic reconstructions through, I don't know, maybe functionality, maximum compression, something like that. So yeah, thank you for your attention. Feel free to contact me if you have any questions or if you want to discuss more. I hope I was on time.
Yes, thank you for the great presentation. Any questions? We can have one question. Okay, very interesting work. So one question will be how, technical detail, how do you decompose the different neural parts to different semantics? So you said it's you do not have any constraints. So I want to, yeah.
No, this is the standard thing. The semanticness is something that emerges. It's not something that we enforce. And I think that this is in principle not very good to do. And it would be nice to somehow think of a way to have this enforced, ideally not through symmetry or something like that. For me, the obvious thing to do is to try to do it with motion, right? Motion automatically infers semanticness because you have the parts that remain connected, that move together across someone across emotion. I personally think that it would be even more cooler to do it with functionality. So there is like this super cool paper from Kai-Chun and Submodules, like the where to act. I really like this paper; it's very cool. Like I think they kind of try to go to the direction of functionality in the sense that you try to reason about like where to act. That would be fantastic. But no. But unfortunately, we do not explicitly enforce it. It emerges, but it would be super cool to somehow enforce this.
Thank you. Thank you for the answer. So I think we can end this session and move forward.
Thanks. So I think the next session will be the panel. So this will be a panel by several speakers that we saw today in the talks, and it will be hosted by Niloy and Shubham. So Niloy, Shubham, if you are here, please take it away.
Thanks, Paul. Yeah, that was a really interesting session. Let's move on to the panel discussion. So we have a really interesting and exciting set of panelists who will be discussing about some of the works they have presented today, but also their thoughts about where this area is going. So let me welcome Shuran, Rusbe, Richard, Daniel, and Tom. I believe you are all in the participant list right now. So as just to start, because people have been going in and out with other workshops running, for each of you to give like just do a 2 or 3 sentence summary of your talks so that we are all on the same page. And then we have a list of questions that we would like to start with. But of course, for those in the audience, if you have questions, please post on the chat and we'll see how it emerges. Okay, so let's start with Shuran.
Hello, everyone. I'm Shuran. Yeah, so a summary of my talk. Today I think the title of my talk was Structure from Action. So in particular, I talk about how we should use robots or agents' active interactions with articulate objects in order to discover their structure. And in particular, their structure is like the part segmentation or their joint access or their joint parameters. Yeah, so that's a high-level summary of my talk.
Excellent. Rusbe?
Hi, everyone. The title of my talk was Learning Visual Representations, Language, and Scene Dynamics via Interaction with the Work. And that's as opposed to passive observation of the work or learning from larger scale data sets. And we showed that there's some promise in this direction. So that's a brief summary of the talk.
And Richard?
Hi, everyone. And my talk was on unsupervised learning of 3D shape structures. And I reviewed what I wanted to call the 3 C's of unsupervised learning. I'm not going to claim that unsupervised learning is the crowning jewels of machine learning, but the 3 C's were inspired from talking about diamonds, right? The 3 C's of diamonds. So the 3 C's are compactness and continuity and consistency.
So it's Daniel and then Tom.
Hi, everybody. I'm Daniel. I'm an assistant professor of computer science at Brown. In my talk, I was trying to convince everybody why I think programs are a good representation for high-level structure in 3D objects and 3D scenes. For a few different reasons, they provide a nice way to, programs provide regularization on high-level structure. They're interpretable and editable. They allow for autonomous agents to do higher-level reasoning. And they have really powerful facilities for abstraction and composition of structures. Yeah.
And my talk was about how to combine ideas from traditional explicit shape representations with implicit ones by using the explicit representation as the substrate for the implicit latent codes, which gives you better generalizability, scalability, efficiency, accuracy, and so forth.
Thanks everyone for the very, very compact summaries. I think it's great to to see the topic spanning from unsupervised learning to neurosymbolic representations to interactions and dynamics, and then also what Tom talked about this multi-scale representation, hybrid representation. We also saw it in Desponia's talk on these neural parts, this thing reappearing again. So please use the chat for questions that you would like to ask the panelists, not just particularly about the specific works they have presented, but future works, future directions, and don't be afraid to ask controversial questions, like if there's fundamentals needs to be questioned. So we'll start with some questions, and Shubham would ask the first question.
Yeah. Thanks again for the summaries and the great talks. And yeah, it's really exciting to have a lot of researchers across sort of vision, graphics, and robotics here. So yeah, again, to reiterate, Niloy, please feel free to ask more questions in chat, but just to get us started, I think the first question I wanted to ask is something that the last two Spotlight talks actually really highlighted, sort of the works from Kyle and Despona, that we've seen this trend of when we are discovering primitives, at one end, we can try to impose both what the primitives are. For example, say that the primitives should be something like cuboids or primitives, or if you're thinking of scenes, something like objects, as well as define the compositional model. And more recently, maybe there's been a shift towards not very strictly defining what the base elements are, but also letting those emerge or be discovered on its own. So at a sort of very high level, the question is, what should we impose versus what should we learn? And maybe there's a trend towards imposing less structure on what the primitives should be. And do you think this is sort of a good trend, or what are your thoughts on the question of what kind of things should we impose versus what should we learn?
Maybe I can go first.
Comment on that?
Maybe I can go first, because I think Kyle is still muted.
Sure, yeah.
Yeah, I mean, I think that for me, one of the coolest things about Kyle's paper, like the structure implicit functions, is exactly what you said, that he lifted the constraints. So I think that this is the way to go, right? Like, I know that there is, like, at least for my case, for neural parts, there was a lot of criticism, like the reviewers, they were saying that, yeah, what you're showing is not really parts, like cuboids are better. I mean, at least for me, I think it's a matter of what you want to achieve. And without a doubt, if we want to have primitives that are somehow geometrically accurate, they need to have more power. They need to be more powerful. So for me, yes, personally, I think the way to go is to lift constraints. And ideally, I would like to have a primitive being a neural network, like NMLP. That would be fantastic. So yeah.
Thanks. Yeah. I also heard someone else trying to say something before. Sorry, yeah, Rusbe, go on.
Yeah, actually, yeah, back in the day when I was a PhD student, so we were working on this compositional models, and so we assumed some primitives. Like, for example, when we want to have a model for a person, so we assume, okay, so the person consists of head, like arms and legs and so on, and then we try to attach these parts together using anagraphs, grammars, and those types of things to create a model for the object. But but it had a number of issues, and one of the issues was that we should not have early commitment to these primitives. I think one of the reasons that CNNs won the game was that they're also hierarchical model, and they are kind of compositional models for the loose definition of being compositional. So the reason that they won the game was that there was no early commitment to any part and or to any primitive, and everything emerged naturally. So that if the goal is to, for example, to improve the performance on object detection, so that's maybe we should not have an early commitment to a set of predefined primitives. But on the other hand, if you want to have an interpretable model, for example, say, okay, so I want a model that detects heads and arms and legs. So separately, I think for that we can make those assumptions. But so basically, the summary of this comment is that it might be better to let the primitives emerge naturally and the structure is learned naturally, as opposed to committing to a specific set of primitives or a specific structure for combining these primitives.
Yeah. Maybe just to sort of probe for a counterpoint, maybe I want to put sort of Daniel on the spot, because he showed this really cool work on more powerful models that build on top of primitives using sort of programs as opposed to maybe just simple composition. So just your thoughts on whether, if we make the primitives a lot more flexible or be discovered on their own, would these kind of programming-based models or ones that learn programs from scratch still be feasible, or it will be just too much flexibility?
I think it's possible. I don't think anyone's demonstrated it yet, but just because all of these like visual program induction systems start with a fixed set of predefined primitives doesn't mean that they have to start with that. I think it becomes a much more challenging optimization problem to jointly discover a set of sort of data-driven primitives, and while you're also simultaneously learning this library of functions over it. I don't think it's impossible. I don't really disagree with anything that Rizbe has been saying. I think to me the power of these sort of more explicit symbols, we'll say, is that people can probably reason about what they are more easily, but exactly what level what kinds you want, cuboids or superquadrics or neural parts, is sort of up to. I'm a graphics guy, so I think about it in terms of what is the person interacting with this going to do with it, right? If our goal is just to get the best performance on some metric like reconstruction accuracy, we're probably fine with whatever. But if we want someone to be able to make modifications to the structures we predict, we want them to be able to draw inferences from them, then I think we maybe do want to impose some of that our own knowledge on the primitives. So yeah.
If I may add, I think there are two sides of the coin, right? So one would be the primitives, and the other would be the operations, right? There's a bit of a trade-off in between. If you want the very simple primitives, then you may want to have more complex set of operations or instructions, if you will, and you can do the other way as well. And I do think that one problem that will be really interesting is to think of primitives in terms of their functions, right? After all, I always believe that ultimately the understanding is at the functional level. And the reason we produce anything 3D is at the functional level, because we want to be able to use it. We want to be able to interact with the environment. So the primitive probably ultimately should be defined in terms of their functionality. There may be some templates of primitives that perform certain functions. And I do think the variety of the functionality is actually less than the variety in terms of topology and geometry. So that maybe there's hope to actually define just a reasonable set of functional templates, and then perform some kind of a compositional modeling and learning on the functional templates instead of focusing on shapes and other things.
Yeah, and I totally agree with Richard. And I think for me, like if I come with like a robotics perspective, I feel I don't really care about like what exactly primitives that we use, but I care about like eventually whether this kind of compositional structure is useful, right? So back to the fundamental question is what kind of structure we want to learn. I think that's really depends on the end application. Ideally, it should be emerged by learning towards the end goal, like whatever the end task that we want to work on. So for example, if I want to segment the object into this set of parts, it's because I want to interact with whatever way, right? Or the reason that we want to define the scene graph this way is because it will help me to navigate in this environment more efficiently. So yeah, I think I care less about like exactly what kind of primitive that we use, but I care more about like whether the end goal is there.
And just to build on both of what's been said in the last few times, I think we over-index in our field on reconstruction because it's a task that we have data for. And so then we start arguing about what's the right decomposition for reconstruction. But most of the tasks are really semantics and functionality, and that any application that people care about. And so we should probably not, we should probably not over-index on reconstruction.
Yeah, and an example for that is like if you think about objects with small buttons, I think for reconstruction loss, those buttons should probably be removed. But for interactions, for a lot of applications, those buttons are very critical to be represented. Yeah.
I think that's a very good lead on to the next question we want to go towards, which is I think many of what you guys are talking about are interpretability with respect to human users. Like in Daniel's case, it's a program that some human would like to change afterwards, right? Or it's a semantic segmentation that a human would look at and try to identify objects or get a captioning or other things for things. But if we talk about some of the ones that Roosevelt showed about the operator not being a human, but another sort of machine or another sort of agent, then is it necessary for the structures to be interpretable by us humans, or is it sufficient for the agent to work on? And if that's the case, do we even need structures? This gets a bit against the theme of today's session, but we would be curious to know your thoughts on that. If the user is not a human, but let's say an agent that can be trained end to end. This was briefly mentioned by Leo in his talk when he talked about this probing. I forget the exact name that maybe Tom would know in early geometry work. These probing from CAD models where you probe for functions or probe for certain attributes rather than the exact shape.
I was going to say that I think I don't fundamentally disagree with anything that Sharon was saying. That when I say that I think we should have these structures be interpretable, that's because the end goal, the end task, the downstream task I have in mind is used by a person, and I totally agree that ultimately the representation should be built to support the downstream task they'll be used for, and that's probably going to be used by some agent, whether that agent is a person or some autonomous agent, and those different agents will have different strengths and weaknesses in terms of what their preferences for input representations are. So that's really what we should be designing for. In terms of okay, suppose your downstream agent can make use of a entangled neural representation that doesn't have an explicit structure. Yeah, that could be the case. I think aside from interpretability, there's some arguments that some of these explicit structures, if we're talking about symbols as opposed to neurons, can be made to generalize and extrapolate better, at least with limited data. So that might be one reason to think about going that direction, but I don't personally feel dogmatic about it.
I think it really depends on the end task. For example, if the goal of that autonomous agent is to communicate with people, I think it should receive some form of input that's interpretable for humans, and also output something that's understandable by people. So I think it depends on the end task. But I guess interpretability and achieving good performance might be competing things for certain tasks. Like for example, imagine the task of object detection. So for distinguishing a cat and dog, or basically discriminating these two categories, maybe it's just enough to look at the head and shape of the ears and so on, and to do this to classify these categories. But if we want to have an interpretable system, that's not sufficient. So we need to have an understanding of the entire body of the animal, so we know which part is what and what's how it can move and so on and so forth. So I think these are kind of competing goals. It really really depends on the end task that we are considering.
Yeah, so I also add one more advantage of why we potentially want like structures in our representation. Even if we consider the end application is maybe like an agent, not human, I think structure or like kind of structural inference is really a good way to summarize like simple rules from very complex data, right? So the example I give in my talk is that if you want to learn how to open doors, and what you basically need to understand is where is the axis and where what's the orientation of the rotation axis, and that's all you need. So you actually don't need to like remember all those complicated trajectories of different doors, different sizes, this and that. So I think that can be like one of the motivation why we kind of want this kind of structure to emerge during learning for the end task.
Yeah, and this I just will say that connects back to the point I was making about these symbols or symbolic rules being able to generalize better, potentially, because if you can compress everything you need to know down to some very simple formula, then if you see something that looks quite different than what you saw at training time, but you can still extract this formula applies to this object, then you can probably handle that new scenario.
So Nilo, I was asking, can we not have structures? I think maybe there will be a day when we don't really talk about structures, we just talk about functionality. I hate drilling on this point over and over again. Many years ago, we all knew this paper called Partial Recognition. The reason we care about structures is we believe that's how people perceive things, right? There's this quote saying that we perceive things by parts and part relations, right? But then if you really think about it, why would one care about whether that's a lever that is a rotation axis and this and that? It's all because they want to use it, they want to interact with it, right? I now really think that we need to understand structures because we need a functionality. That's ultimately what matters. And structures are there because structures are about parts and part relations. And they are there just because they are there to perform certain functions. And it doesn't matter if it's a human or it's any other agent. And the question, can we not have functionality? I think the answer will be no. To live, to be in this world, we need functionality. And the agent can be whatever.
Mm-hmm. Yeah, thanks a lot for the thoughts. Actually, we have a question from the audience, but maybe before that, I have a question which is actually very related to the discussion we've been having. And sort of Tom and Shuran also mentioned some things along these lines that, Shuran gave the example of the reconstruction loss won't really care about the small buttons. So I think a lot of us are coming at this problem of inferring structure from maybe a computer vision background, but some of the speakers here have been doing a lot of exciting work in robotics. So my question is more, have your perceptions of what kind of things are important changed over the recent years once you've started looking at more robotics problems? And are there things you would wish the people in computer vision who don't really think about these would start focusing on?
I can start. I kind of feel one of the things I learned is that the task is actually, so if you consider active agent, consider like robot is part of the picture, the task of a lot of computer vision tasks is actually simpler, not harder than what we think. So I think one of the points that Hao made in his talk is that if you consider interactions, you add the temporal dimension, you have motion, and therefore the problem is harder. I think that's true to some degree, but also a lot of times if you have an active agent and if you can interact with this world, a lot of problems become a lot easier. So for example, in like for object part segmentation, there's a very messy problem of like how you define parts, right? What is a meaningful part? But I think in an interaction perspective, the motion of the objects automatically defines what should be a meaningful part. And by observing the motion, a lot of times the part segmentation problem is trivial. So yeah, so I think that's probably one of the most important lessons I learned.
Yeah, something and related to the previous conversation is that it depends on the task. I mean, there's a lot of tasks that in recent years and work that we've done. So you can go pretty far with pattern recognition without really understanding structure. So an example of grasping objects with a robot arm, it just turns out in the setting that a project that Sharon did, it was just it was possible to just look at the patterns of what you observe and find a good way to grasp it without actually doing a 3D reconstruction, understanding the pose of the object, planning a grasp and all that. And maybe it was even more robust to just go end to end from observation to whatever, and you didn't understand any structure. And so I think there are tasks, if I had to like learn what would this one object look like from the other side, then that's something you have to really understand structure for. But there's a lot of tasks that you don't. And there's probably also a lot of animals that operate just fine in the world without understanding structure. Like at ICRA a few years ago, there was a talk about how bees operate in the world. And it seems like it's all pattern recognition and optical flow, and they can do everything they want just from that. And I might be incorrectly summarizing that talk, and I apologize to the speaker if I was. But anyway, so I think there are complex tasks that are probably more complex than the ones that we usually work on that require structure, but I think a lot of things don't. That would be, if all you care about is can you operate in the world, I think you can go pretty far with pattern recognition.
Thanks. Anyone else want to add on this? Or
regarding your question, Shubham, so what you want to do differently? So in computer vision, we usually rely on larger scale data sets and learn from a lot of data, but that might not be necessary in certain cases. For example, I want to know how to move this object, maybe by simple interaction with that object, I can learn that, like with just very few examples. We don't really need to have a larger scale data set for that. So that's, I think, probably we should move towards like few learning from few examples, like, because some of these tasks are very simple, and like if you want to collect a larger scale data set for each of these tasks or each of these primitives, probably it will not be scalable, and probably we need to learn by few examples, by just few interactions, and move in that direction.
Yeah, thanks. So as in, I guess the learning setup or paradigm itself also should be re-examined and not just representations. Thanks. Actually, so also have maybe one question from the audience, which I want to pose to the speakers. So the question is, how would you compare challenges between the two problems? One being segmenting a shape into semantic parts, and the second being synthesizing a meaningful object from parts. Which one do you think is more challenging? So again, the two problems being, given a shape, we want to segment it into parts, versus we want to be able to synthesize possibly new objects in a part-based way. And
I think it depends on this, since you were just mentioning the learning setup, I think it depends on the learning setup. If you assume you have lots of labeled data, I think these days, both of these problems are about equally as challenging. We've seen, pick whatever metric you want. People can do really good part segmentation, supervised part segmentation, and we have models that do really good part-based generative modeling as well. So I think maybe the question might be, where it gets interesting is what happens when you don't have as much supervision and you're trying to do either the segmentation or the part-based generation using some sort of other proxy, something about functionality, for example, like Richard was saying. I don't know. I don't know what the right answer is there. I don't know what other people's thoughts are.
So maybe sort of my own interpretation of this, especially in the context of not having supervised data, a lot of the approaches we saw today did discover these semantic parts through generation. And is that something we feel is critical if the goal is to just say segment?
I mean, I think what we're getting at is that, so discovering parts without supervision, we have to discover them with respect to some other proxy task or some other downstream task. And so far, it seems like what we've done is reconstruction, which is, or as a form of essentially generating a shape with these parts. But we've heard other people talking about how ultimately we'd like to move beyond that. We'd like to be able to say, okay, can I propose a part without supervision that doesn't just reconstruct the shape well, but also reconstructs the ability for me to articulate some sort of articulative motion well, or that it, maybe it expresses ranges of deformations that I typically see in related types of shapes, like the fact that these parts tend to sort of co-vary across a data set. Then we're starting to get more towards this idea of functionality that Richard's talking about.
Yeah, thanks. I think Niloy had a few more questions to ask, but in the meantime, again, just a reminder to the audience to keep posting, and we're happy to ask.
There's a lead-on question that we can ask, and it relates to the very cool set of work that Richard presented on this unsupervised learning, and it talked about the 3 C's there. Now, I was wondering, like, maybe there are 2 levels of supervision. One is we give supervision in terms of annotation data, etc. But there is another level of supervision which we also give, at least as I see, in which data set we are learning on. So something that Shura mentioned about this case of the buttons on a remote or something, which is a small one. So we have to be, it's not expected that if we just randomly sample or observe this, that this may not be observed, but it's functionally, it's very important. So just the act of gathering the data, there is a hidden level of supervision that we don't talk about. So when we go beyond semantics to a functionality of the object, what is the right sort of mechanism to ensure that we have a good sort of distribution of data? And maybe this is our fairness of data in the world of 3D geometry, where do we have all the modalities correctly captured? So thoughts about this, because we have a range of application experts here from vision, robotics, and graphics. I'd love to hear your thoughts on that.
I guess I would say, I guess you do have to make sure that the data you train on is sufficiently granular for the thing you're going to use it for. So like the example I always think of is, I suppose I have a data set of objects, synthetic objects, and I'm going to try to train a robot to understand how it can manipulate these things in terms of what parts I can interact with. And if we're trying to teach a robot how to open drawers in a cabinet and put things in them, I can't do that if my 3D models don't actually have cabinets in them. And this is like a surprisingly large number of objects in common 3D object repositories for which this is true. There are a lot of objects, say in ShapeNet, that are basically just textured boxes that don't actually have any of that detailed geometry. So that's maybe sort of the obvious answer, but that's where I'd start with this question.
Yeah, another thing I would say that it's quite important to consider like active agents while you are collecting data. I think it provides a lot of benefits. Like first of all, it can generate actions. As we see that motion actually helps people to help agents or people to understand the structure or the part. And also, I think having actions also, another layer is that we can learn the causal relationships, right? So for example, the button example, I'll go back to that. So for us, we learned that button is something pretty critical because it causes some special effects. It turns on the TV. And then I think that kind of information is something we can only gather or like those kind of supervision we can only gather if we consider active interaction. Yeah, so I think a critical thing that's we should consider, but I actually feel it's also very challenging to get is like consider active interaction, especially hard if you consider real world data collection.
So when I'm thinking what Niloy is saying, supervision, somehow this term of handcrafting just keeps coming to me. It looks like we have this evolution from handcrafting features, and now we're mostly handcrafting network architecture, and maybe there is this handcrafting of data. Right, so maybe that's kind of the supervision. What kind of data you prepare. I do think that's something really to think about, right? Now I think what's happening right now is just to collect lots of data, and lots of data are actually redundant, and that redundancy actually can hurt your learning algorithm. When we teach our kids or teach whatever agent a task, we actually we're very selective on how to teach them, what data to show them, right? We don't just like throw everything that we can possibly obtain or can possibly acquire to them. So maybe if my understanding of the question is correct, that indeed thinking about how to handcraft really nice data to supervise is actually very important, right? That actually addresses the issue that you don't need lots of data, right? You just need the very, very valuable data. So maybe some handcrafting and that level of supervision indeed is highly desirable.
Maybe I'll just add one more thing to the mix. We talk about a lot of time. We talk about kids and how they learn. And Richard, you mentioned this, but kids live in a real world. So when they interact with it, the physics is always there. But in the interaction setups that Roosevelt presented or Shuran presented and other things, my understanding is we're still not quite there in simulating full physics when we don't know the full scene. And that might be partial observation, partial parameters, partial materials. So there is maybe this gap, and that's maybe the part, Richard, that's preventing us to go directly to functionality, because we can't do the full simulation with the imperfect or incomplete data we have, incomplete at various levels. Right. So any thoughts on that, or that's maybe not really a problem, or it is a problem? What do you guys think?
Yeah, ideally we should collect data from the real world, but usually due to mechanical constraints, the speed of data collection will be very slow. We cannot collect too much data using real agents in the real world. On the other hand, we have these simulators that and our hope was that we can make something similar to the real world in these simulators, but we have to sacrifice a number of things. Like for example, our physics is not super accurate. Our appearance is not like photorealistic. So there are some things that we need to sacrifice. But yeah, there's always this trade-off. Like, do we want like super accurate, realistic data, or we want something which is not accurate, but it allows us to collect a large, a diverse set of interactions, and in a short period of time. So that's there's always this trade-off.
Yeah, I think it's interesting to think about, let's say hypothetically we had perfect simulation environments. Would we then just train our agents to operate in those environments functionally, and all the structure that they care about would emerge? And probably, I mean, if we had good optimization techniques and so on and so forth. And an example of that, I think, is in navigation of indoor scenes or something like that. You have environments like habitat and stuff like that, where the simulation is good enough for navigation, visual observation. You don't really have to interact with anything except collide with it. And agents are able to learn extremely well to navigate just by exploration. And so could we produce simulation environments that go beyond just navigation and allow students to learn on their own? It's a kind of an interesting direction. And I know people that are in this workshop are working on that, like how as Sapien and so on and so forth. Yeah.
Yeah. So actually this discussion on interactive ways of learning, or how biological agents learn, is also a good segue to another thing I wanted to ask, which is, through a lot of talks today, I think we heard examples of biological agents. For example, Roosevelt was motivating with how kids learn, or sort of how Sue had some examples of humans being able to generalize, or Tom was mentioning the kind of representations that bees might have. So just at a very high level, wanted your thoughts on whether we should pursue the kind of structures that we think perception systems of these biological agents have, or not really, as in, are there some perils in doing that, or it's almost always a good idea to try to mimic those?
I think we probably don't really know like what kind of structure we use to represent this word. I think that by itself is a very, very, very challenging question. Otherwise, we can just directly copy that. All right.
Mm-hmm. Fair enough.
I think
Yeah.
it's like well, I was going to say we have, we're trying to optimize some objective with, so say it's some task objective, like solving some interaction problem in the world. And the biological structures are sort of optimized by evolution, but evolution is not really optimization. It's like it produces systems that are just sort of just good enough for the local niche that they're in, but they're not necessarily the best that it possibly could be. So it's like, if we find some problem that it's really hard to solve, and we don't have a good idea of how to formulate the correct objective that we can then optimize with tractable optimization algorithms to sort of solve it from first principles, then maybe you might not be too bad off to just say, I'm just going to copy what evolution did. But I think if we have, if we can formulate the problem in a way that's well formed and admits tractable optimization, you should probably just try to solve it from first principles, and you might find something that works better than what evolution discovered for that particular problem or for your particular domain, because your agent or your setting might look a little bit different than what that critter was having to do out in the real world.
Yeah, and I think it's unrealistic to think that the limits of a computer are the limits of a person. A person has biological constraints that a computer doesn't. A computer can start at birth from all knowledge any other computer has ever acquired. It can shoot that light out in the environment and measure how long it takes to get back. It can communicate instantly with other computers and unambiguously. There's just all these things that machines can do that people can't for biological reasons, that to think that we should mimic what people do and that's the max we could ever get seems ridiculous to me.
Add on to that, I kind of feel like it's probably not just biological agent, but in particular for humans, if we're dealing with human environments, actually, because it's designed by humans, so we have some structure goes into it when we're designing it. So maybe those kind of structure can be like leveraged or used for robots as well. Yeah.
Yeah, there's always this example that airplanes don't flap wings. So there is some evidence that that we can do better than biological systems, but that's a tough question. There are a lot of unknowns we don't really know.
I think once I visited Andy's lab at Imperial for his robotic simulators, and he mentioned one thing that I remember very well is, like, as humans we're used to grasping, right? But for industrial application, often they would just have a suction or a vacuum that would just come and entirely sidestep the grasping problem, and that's maybe a kind of like what the agent can do. And we, like as Tom mentioned and Rusby also mentioned, we don't have to limit the agent just because as humans we do this. So maybe that's a good sort of lead on to the next question that we were discussing, is how about the choice of representation? So we saw SDF, hybrid representation, Tom mentioned about that, BSP, Richard mentioned about that, and other types of meshes, point cloud and other things. So do you feel like the choice of representation are the ones that we impose in the first step of setting up the problem influences what type of structures are easy to discover or not? Or is it something we should give more thought towards? Because I know this representation question comes up like almost every talk and over decades. So I'd love to hear if there's any sort of resolution to this. Maybe you can give some examples from the your favorite representations. Maybe that's a more specific question, and I think we will have a mix of choices among the people in the panel.
Maybe I can comment on that. So ideally, the representation should be general enough that's suitable for many different tasks. Like if I want to do object detection, if I want to do a slang, if I want to do object interaction, so it's some form of representation that's suitable for all of this. But I think coming up with that representation probably is very difficult. So and what we have been doing so far is, so we target a specific task and we try to come up with a good representation for that task. I think we have been kind of successful at that, but coming up with a generic representation that supports like many different tasks with very different nature, I think that's still an open question, and we don't really know how to do that.
Yeah, I think indeed what would be the best representation really depends on the task. A neural implicit had come along really because of its learning a continuous function. It may not be the best representation for, say, manipulation. I would go for primitives with the relations. One thing that reminds me is that there's a lot of recent talk about like digital twins, right? So digital twin, of course, is you have a physical reality and you have a virtual reality. I think maybe we should really have representation twins, right? So basically you have you can easily convert between different representations. Really depends on your task, right? You can easily convert, like say, point clouds and primitives and neural implicits. If that is possible, then that's the representation, right? It's kind of like a hybrid representation. But the key thing here is that you can so quickly, so naturally to convert between any two or any pair of representations, like you know. So that may be the way, so that you can have a representation that is like a hybrid, but it can really just be easily picked, like which version of it, which reality of it that can fit for a particular task. I think hybrid is probably a start, but maybe some kind of a representation twins can be thought about.
A quick call out from here. So Ethan says on the chat that semantics will always be dependent on the use case and the agent. So any situation where semantic decomposition is being applied will have to consider the context that the object exists in. So I think that's very much true, right? And it also relates to the object usage and the functionality as we've been discussing.
So actually, given we only have a few more minutes, I wanted to ask a slightly broad and vague question, which is, a few decades ago, the field of AI was very much into symbolic reasoning and symbolic representations, that you'd have these high-level representations, you would plan with those, manipulate those symbols. And when we talk about imposing structure in whatever form, that there are these primitives or imposing some different forms of functions, different operators, it evokes some of those sentiments to me. And so I guess the question is, are we sort of repeating the same maybe mistakes a few decades later, or is something very different in our current pursuit of more structural representations?
I guess I'll jump in on this one first, because I guess this is kind of getting at this new, I don't know, there's a new wave of people working on these neuro-symbolic representations. I guess I'd consider myself part of that movement. Yeah, so I think that I wouldn't necessarily say that it was a mistake in the past. I think that the sort of good old-fashioned AI folks were only able to get so far because they thought, everything was deterministic rules, everything was expressed in pure symbols, and some things work well that way, but we also know that we need to be able to have probabilistic reasoning, and we also need to be able to have these, now that we have these neural nets that can make these, can learn these like really, really sort of fast function approximators. So I don't know. I think it's like, I don't see any reason to be dogmatic about any of this. It's just, we have a bunch of tools that are all good at different things. And to me, it sort of feels like I'd love to have like, the one system to rule them all that kind of combines the strengths of all of them, right? So you have something that uses neural nets to say do like raw perception to extract maybe some sort of primitive, we talked about this, like primitive elements or primitive combinators, and maybe it does that in a probabilistic way. And then we have something that reasons symbolically to combine those primitives into some representation that can be acted upon, can be manipulated, can be support extrapolation as well as interpolation. That's where I sort of see this going. So I think I look at it not so much as like, are we repeating the mistakes of the past, so much as how do we borrow what was good about what was done in the past and combine it with all the things that are great about the systems we have now, these neural systems.
Yeah, maybe we should also not forget that maybe 15, 20 years back, people thought like CNN was a bad idea or neural networks were a bad idea. You see where we are now. So we can look ahead with a positive outlook. Shubham, how are we doing with time? We just
I think we have about 3 minutes, so maybe we can even just wrap up a bit.
We can make it open now for the panel members if you want to say something.
If they have any comments.
All focus our research on, or something we should stop doing, or any thoughts, anything that's exciting.
I mostly want to say thank you so much for organizing this panel. I think you guys did a great job. It's very interesting. That's my final thought.
Thanks, John. Okay, I think maybe we can then wrap it up a bit earlier. Thank you everyone for attending, especially the speakers and the keynote speakers and the spotlight speakers for participating. I think Kai-Chun wanted to, again, do some logistical announcements, so I'll hand it back to him.
Thanks, everyone.
Thanks, Shubham. Thanks, Inoy. Thanks all the panelists for the fruitful discussion. And thank you for joining us today.
Thank you for organizing it. Thank you. Bye-bye.
I just want to say here, because I see Kai-Chun here, that let's also thank all the organizers, especially Kai-Chun and his team who did all the hard work in putting this together. And Kai-Chun, you would probably introduce the last poster session now and how we'll get there. Yeah, so over to you.
Thanks. So thanks all the speakers today to pulling out 8-hour-long talks, and we actually have 16 talks for today. If you are not too tired, we still have the last poster session. So we have 14 paper authors are waiting you in the gallery. So I just post the link in the gallery, and let me share my screen to give you some instruction of how to join the gallery. So we have 30 minutes left for the final poster session, and we are and there are authors presenting 14 papers with many great latest research works, and we are using Gallery for it. So this is the link, or you can just scan this QR code to get inside the Gallery. And so what you are going to do is to first set up your name and video and audio setups. And then you can navigate to the elevator. If you are starting from anywhere, you just navigate to the elevator, and then you can select our workshop, the Structural and Compositional Learning on 3D Data workshop. And you click it, then you will be hopped into this space. So you are seeing there are already authors waiting in front of the 14 papers. So we have 14 papers in total. So you can check the paper IDs from the workshop website by clicking the papers tab. And you can see that we have 3 archival 8-page long papers and also 11 short paper presentations. So they're all pretty good papers. So please make sure that you spend some time to talk to these authors. So for each paper, there is an ID. So there will be one author waiting in the gallery to meet you for your questions. And for each paper, here are the authors, and you can click this button to see the paper, or you can see this, click this video button to see the video prepared by the author presenting you the work on YouTube. And also you can click this button to see the abstract if you want. Okay, so please come to the gallery session and ask questions to the author.